Hi, welcome to chapter 15. Aren't these so much fun? So today I'm going to tell you that everything I told you in the first part of the year was a little bit of a lie. That's terrible. So whenever I would draw an equation on the board, I would always draw an arrow that looked like this. But that's kind of a lie because every time that there's a reaction that goes together, you have your products or your reactants that mix together and turn into your reactants. That's true. But also, this reaction also happens. There is a forward reaction and there's a reverse reaction. That's what I never really told you. So today we're going to talk about the forward and the reverse reaction. And believe it or not, if you did your lab already yesterday, or watched the lab anyways, they were talking about equilibrium. So equilibrium is when the forward reaction and the backward reaction happen at the same rate. So last chapter we talked about rates. Now we're going to talk a little bit more about rates. So in this reaction you have this NO2 gas plus carbon monoxide gas turns into nitrogen monoxide and carbon dioxide. They're all gases. And so as this forward reaction is going, once you start to make some products, the reverse reaction also goes. And when it happens at the same rate, that's called equilibrium. So you have, they have some graphs. I'm not going to try to draw the graph. On figure 15.1, you have this chemical equilibrium happening. So you have the forward reaction and the reverse reaction, and once it hits this spot here, that's where equilibrium is happening. So this is figure 15.1 in your book. So equilibrium. So you might want to get used to seeing kind of graphs like that. We're going to look at a couple more graphs, but so chemical equilibrium. And when we did the lab that was on YouTube, they also said that some reactions can be more weighted for the product side, and some reactions are actually weighted more for the reactant side. So we're going to find out today about how to figure out the equilibrium constant. So we've done before any reaction A plus B turns into C plus D for any reaction. We did the rate reactions last chapter. So this one, we're going to figure out the K, also the equilibrium constant. But these reactions, you only have to figure out when they start giving you numbers, you only have to pay attention to the ones that say at equilibrium. So the equilibrium constant, K, is equal to the products divided by the reactants. And this time, it's even easier to figure out your exponents. Last time it was kind of a pain to figure out your exponents. You had to look at trials. This time you don't have to do that at all. So this time you just have to look at your chemical equation. So for all of these, your rate constant at equilibrium is going to be your concentration of C, whatever this is, to this exponent, whatever your stoichiometric coefficient, your big number is, plus times your concentration of that to this exponent, divided by the concentration of this to this exponent, times the concentration of B to this exponent. So now you don't have to calculate your exponents anymore. They come from your stoichiometric coefficients. So much easier, yay! The problem is sometimes you're going to get really big exponents. So the trick with these problems are going to be figuring out how to use your calculator. So you need to make sure, especially when you have really big exponents here, that you know where your button is. Maybe y to the x is maybe what your button on your calculator looks like. So to the 8th power, to the 7th power, to the 6th power. So you might want to get used to doing exponents in math. All right, so let's do example 15.1. If I could edit these things a little better, I would cut and just write it, but oh well. Example 15.1 on page 496. We have N2 gas plus O2 gas turns into 2NO, and that's a gas. All right, so I always have a tendency to draw my arrow that way because usually we are worried about the concentration to get the reaction going forward. But we're going to see what our arrow looks like. This means forward and backward reaction. So it says it reaches equilibrium when the concentration of N2 is 0.354 molar, concentration of O2 is 1.124 molar, and the concentration of NO is 4.51 molar. What's the equilibrium constant for this reaction? Easy. So at equilibrium, it's going to be the products, which is NO to this exponent over N2 gas to this exponent, which is 1, and O2 to this exponent, which is 1. So now I just drop in the numbers. So it says that N2 is 0.354 molar. O2 is 0.124 molar, and NO is 4.51 molar. So the trick here is watching your units. So you're going to have m squared on the top and m on the bottom. So they're actually all going to cancel out. So if you put this in your calculator, you put 4.51 squared divided by, make sure you use your parentheses, 0.354 times 0.124 end parentheses equal, and you should get a K of 463. I would pause here, actually put that into your calculator and make sure you're getting it. Because if you get this wrong, it's not going to be because you set it up wrong, it's going to be because you didn't put numbers in your calculator right. So, do you think this is a big number or a small number? I think 463 is very big. What does that mean? That means that this reaction mostly goes this way. It makes a lot of products and only a little reactants. So this is weighted towards the products. So really I could truthfully write an arrow that goes this way. Okay? So if I get a K that is very small, that means my products are small and my reactants are large. That means my arrow really goes this way. That means it's weighted more towards the reactants. If I get a K that's around 1, that means I make just as much products as I do reactants, and so that means I should really have an arrow that looks like this. It goes that way and that way, about the same. So if my K is large, I'm going to draw an arrow that way. If my K is small, I'm going to draw it that way. And if it's about 1, I will draw it in both directions. Okay, hopefully you can see that, both directions. Okay.